We want to talk today a little bit more about Newton's equation. It's just force equal mass times acceleration. Now, the reason I've been wanting to talk about this is, for one thing, I want to address the mass. We talked about the metric system and how meters and kilometers, which are 1,000 meters, and millimeters, which are 1,000th of a meter, and centimeters, which are 100th. So we talked about meters instead of inches, feet, and yards like we have, and miles. We talked about liters, I think, in terms of volume instead of quarts and gallons. So a lot of people, when they see mass, and the units for mass are kilogram, which is 1,000 grams, or gram, or milligram is 1,000th, or microgram, millionth of a gram, in the metric system, then you might tend to think, okay, that's the same as weight in the English system, or pounds. And it's not. There's a difference between mass and weight. So that's what is important to understand. But for now, to get you started, you can think about mass as how much of something there is. And if you measure two things, one has twice the mass of the other, and you measure them in the same location, like your kitchen, then the more massive the second object is, the more heavier it will be. In matter of fact, if it's twice the mass, it'll be twice as heavy. Now, that's not the same as bigger. It can be bigger and lighter. That's not more massive. But if it's bigger and heavier, it's more massive. And that's only true when you measure them in the same location. And this is why we want to talk about the difference between mass and weight. Because if you take the second one that's twice as massive, twice as heavy in your kitchen, and you take it up to the moon, the mass is going to be the same, but it'll weigh less. So only if you are measuring in the same spot, then something that's twice as heavy, you could say is twice as massive. It's proportional. So having taken care of that, the next thing we got to look at is acceleration. And I know you understand sort of what acceleration is. You hit the accelerator on your car and your head slams against the headrest. But we want to talk about a little more scientific terms. And to understand acceleration, you have to understand velocity. So we're going to talk about a little bit of both. But if I told you you were going to visit a friend that was 300 miles away, and it took you 6 hours to get there, and if I asked you, so how fast does that mean you drove? And you said, well, 300 divided by 6, that's 50 miles an hour. You'd be wrong, because you don't know that you drove 50 miles an hour that whole time. You might have stopped for dinner for an hour and then drove twice as fast to make up for it. You might have gone to a city where there's traffic lights, so you had to slow down. You may have been out on the freeway where there were no cops and you went 90 miles an hour. So when you say that you went 300 miles in 6 hours, that's an average of 50 miles an hour. Sometimes faster, sometimes slower, but it's an average. Well, you cannot predict with equations and graphs something that changes all the time. Let me jump in here and clarify that what I mean is, if it's a random change that you cannot predict, then you can't write an equation or formula for it. If it's a repetitive change, something that occurs over and over and over repeatedly, then yes, you can write an equation for it. So we're going to back up a little bit and talk about something instead called constant velocity. And like the constant, when we talked about variables, the constant don't change. This implies that your velocity doesn't change. Now, before we talk about velocity anymore, you've heard me say that a couple times now. Let's quickly, and then you don't have to remember this until, you're back in studying this again. But basically the difference between speed and velocity, both these cars, for instance, are going 25 meters per second. They're going the same speed. But velocity, when scientists talk about velocity, they refer to the direction. And if you're going on to the positive side of your number line, then it's a plus velocity. And if you're going toward the minus side of your number line, it's a minus velocity. So the velocities are different. One's plus and one's minus because they're going in opposite directions, even though their speed's the same. So like I say, I wouldn't worry about that right now, okay? For right now, when you and I are talking, speed's going to be the same as velocity. I use the word velocity because it's a more scientific term, and that's what I'm used to. So when we talk about a constant velocity, here's a graph. And you see, instead of an X on this side of the graph, we have a T for time, and the time is in hours. I'm showing the units here. Velocity, I forgot to put that in parentheses, is in miles per hour. And if you look, you're always going 50 miles an hour. It never changes. 1 hour, 50 miles an hour. 2 hours, 50 miles an hour. 2.5 hours, 50 miles an hour. 2 3/4, 50 miles an hour. Don't matter how long you're looking at, it's the same. You're going 50 miles an hour. It doesn't change. And velocity then is measured in meters per second. How many or miles per hour or feet per second or something like that, depending on if you're in the metric or the English system. Now, acceleration, this would be the graph for acceleration. And we still have time, but they changed it to seconds on this one, and I left it there. And they had this one as meters per second, so I left it there. Well, basically what you're seeing is that you start off, you hit the gas. In 2 seconds, you're going 6 meters per second. In 4 seconds, you're going 12 meters per second. In 6 seconds, you're going 18 meters per second. So every second, you're going about 3 meters per second faster. So since you're going 3 meters per second faster every second, you would write that as 3 meters per second per second. Now, and I use parentheses so you can keep track of, since the divide sometimes is in. So, well, what we have is, as we said, 3 meters per second, or however many meters per second, divided by seconds. Well, from your algebra class, you should remember that you could put this S over a 1, and it's the same thing. So you would have 3 meters per second divided by second over 1. And when you divide by something, it's the same as multiplying by the reciprocal. You remember that from your math class. So if it's the same as multiplying by its reciprocal, you have meters per second times 1 over second. So it's meters times 1, meters on top, seconds times seconds, seconds times seconds on the bottom. And another way to write that, when we have two things multiplied the same, two things multiplied together, it's written as S with a little 2 up top. Now, since I can't do that on the computer, this is a shortcut we use, the caret sign and the 2. But it means S squared, or S times S. So meters per second, you'll hear people say meters per second squared, and that's the same thing. So, guess what Newton figured out? Or was this one Galileo? Okay, I figured out later that it was Galileo and not Newton. Was when you drop something from a cliff like this, it doesn't go at a constant velocity. 1 second later, 10 feet, 2 seconds, 20 foot, 3 seconds, 30 foot. It goes faster and faster. It accelerates. And by the way, if you slow down, that's called deceleration, which is the same as acceleration, but in a minus direction. So it's still acceleration, but it's another name for it would be deceleration when it's in the negative direction. Anyway, it goes faster and faster and faster when you drop it. Now, here somebody was able to measure this. So apparently he did not drop balls off the edge of a building. Basically, he used an inclined plane such as this, where he could adjust the amount of incline and use the data that he could then accumulate to determine that the acceleration of gravity was a constant. And found out that in the first second, it goes 9.8 meters per second. After 2 seconds, it's going 19.6 meters per second. After 3 seconds, it's going 29.4 meters per second. So every second, it's going 9.8 meters per second faster, which means it's going 9.8 meters per second faster. That's the acceleration. And that doesn't change when you're in the same spot. When you go to the moon, and this, by the way, this is what we call gravity, when the acceleration goes faster and faster due to gravity. But if you go to the moon, gravity is 1/6 of what it is here. So the acceleration is 9.8 divided by 6, or 1.5. So this is why it's important to what we talked about. If you're in the same location and gravity is the same, then you have the same acceleration. And so going back to Newton's equation, you could replace acceleration with gravity. The force pulling you down, the force of gravity at sea level, is always nine 0.8 meters per second. Or, in our English system, that's second squared. 9.8 meters per second, or meters per second squared. In our English system, it's 32 feet per second squared. That's what gravity is. And so the force pulling you down, the other thing, the name for that when we're talking gravity is weight. That's where weight comes in. Your weight is your mass times gravity. It's not mass, it's proportional to mass. It's mass times gravity. So if you have a 1 kilogram mass and you're at sea level where the acceleration of gravity is 9.8, you have 1 times 9.8 equal 9.8 newtons. That's what they call it instead of pounds. Newtons of force or weight. Now, of course, we use pounds instead of newtons. So if you divide say you're 100 pounds, and you divide by 32 feet per second squared, that gives your mass. The mass in our system, instead of kilograms or grams, this is funny, is slugs. Never heard of slugs? Yeah, we don't use it. We don't talk about mass. We talk about weight. We don't talk about mass. So the funny thing is, when you talk about mass, you go to the moon, your mass is the same, your gravity is 1/6, therefore your weight is 1/6. When we say, okay, you weigh 50 pounds, how do you know if they mean at sea level, on the moon, 2 miles up in the Himalayas? You don't know. So what we do, just to avoid confusion, is we assume you mean at sea level. If it's measured somewhere else, the weight is less up higher and more down lower, like in Death Valley or down the bottom of the Grand Canyon. You might notice you're a little heavier down there. We assume it's measured at sea level, unless if it's measured somewhere else, you tell the person. Two things that are really interesting here. The first is, I don't know how Newton figured out that force equal mass times acceleration. Remember, this guy, there's no TVs, no internet, no lights even. They had candles back here. He's sitting there at a table with 2 balls. And here's the thing. Remember, if you don't have any acceleration, you can still be going a constant velocity. You could be going 50 meters per second and not accelerating. So acceleration is 0. 0 times anything is 0, so the force is 0. Which means if you don't have to push, you don't have to apply a force on that ball for it to go 50 meters per second. You don't have to add a force to it. It'll keep going forever with no force on it. Now, of course, you know that's not true because it slows down and comes to a stop. Well, that's because there's a thing called friction. Friction, when it bumps into air molecules and when it rubs on the table, friction is what causes it to slow down. We have friction here. There's no friction in outer space. He didn't know that. He was never in outer space. But somehow he knew that if something is going at a constant velocity and not accelerating, it doesn't need a force to keep it moving. And this is the exact reason why satellites can orbit the Earth and you don't have to go up there and refill them with gas every so often. They just keep moving forever because there's no friction up there to slow them down. They just keep on going and they keep on going. That is really neat. So part of the explanation was this incline ramp we looked at earlier that they used for their experiments. And while this particular replica doesn't look like the angle is adjustable, it is my understanding that the one that they used, or that the ones they used, were, and that by observing the differences in the acceleration based on differences in the angle, they could determine what the acceleration would be if the ramp could be placed entirely uh, vertical, such as would be the case of a falling object under the acceleration of gravity. But I also believe that some of the experiments were conducted with models that did not have this stop plate here, because I have read that while they observed that the acceleration would vary based on the angle, that the ball in all cases would continue to roll off a certain distance before stopping. And no matter how close they try getting closer and closer and closer to, making it level, and no matter how close to level they got it, the same thing would happen. The ball would roll off the same distance. And so, again, from that is how they realized that if it was perfectly horizontal, in other words, there was no gravity, no acceleration, that it would continue having a constant velocity. So that explains part of it. Now, consider also that in outer space, they always assumed that it was empty, void of any matter, uh, perhaps filled with ether, but not matter. And so the amazing thing isn't so much that they realized that it would move forever at a constant velocity in space where there was no friction. The amazing thing to me is that they figured out that it was friction in the first place that, caused it to come to a stop, here. And the reason that's important to me anyway is that except for this realization, the formula would be force equal mass times velocity instead of mass times acceleration, because they would have believed that it would take a force to keep an object moving instead of only taking the force to accelerate it. So the difference, mass times velocity, and instead they realized it was mass times acceleration. But the other thing that's neat is if you were standing here on the Earth with this cannon and fired a cannon, and normally, cannonballs don't go very far, it would follow this path A and come and land somewhere. You shot it a little harder, it might come out further and land somewhere. If you could really shoot this thing, and I'm telling you, it would have to be a pretty powerful cannon, but we could do this with rockets where they go so fast that gravity cannot pull them in. Remember, gravity's pulling inward on this all the time, but gravity can't pull it in. It's going too fast, and it could fly off into outer space. So the trick is they find a specific speed that they could shoot that at, a certain velocity that's not too little and not too much, like Goldilocks. It's just right. And so what happens here is the ball is pulled in by gravity, okay? But what's happening is the Earth is curving away at the same rate as the ball is dropping toward the Earth. So it's actually dropping toward the Earth, but the Earth is moving away from it to match it. And you can rotate it. The same thing happens here. It's falling toward the Earth. I guess we're looking at this line. It's falling toward the Earth, but it's not going so fast it's out here, and it's not going so slow that it hits. It's going just right to where the Earth is curving away at the same amount that it's falling. And we keep going around and around. So this is exactly what's happening. That planets can orbit the sun, the moon orbits the Earth, we send satellites up. We don't need the gas because they just keep on going forever, but they don't fall and crash to the Earth because they're going at just the right speed, and they calculate, scientists figure out the speed. So when they let go of the satellite with a rocket, let go of it, it's going just the right speed that it can keep going around and around, and it's falling toward the Earth, but the Earth is curving away the same amount so that it's just going round and round and round, and they keep going. I think that is really neat. And all of that, somehow Newton, sitting in his candlelight, figured that out without ever being in outer space. That, to me, is amazing. Talk to you more next time, bud.